The problem studied in this paper is to estimate the motion of a moving target object using a moving molecular camera. This is a fundamental problem in many tasks such as vision-based autonomous driving. Our research is particularly motivated by vision-based aerial target pursuit. The conventional bearing-only approach merely uses the bearing information of the target obtained from vision. This approach has been extensively studied so far. The limitation of this approach is that the observer is required to maneuver in the lateral directions to enhance the observability. However, the required maneuver may conflict with the desired motion of the observer in many tasks. Can we enhance the observability and, in the meantime, do not require extra motion of the observer? This is an important fundamental problem. We notice that, when a target has been detected in an image, we can obtain a bounding box that surrounds the target's image. The bounding box carries two types of useful information. The first is its center point, from which we can calculate the bearing vector pointing to the target. The second is its size, which is a joint function of the target's distance, target's physical size, and the orientation of the camera. Up to now, the bearing information has been extensively studied. However, the size information is valuable but has not been well explored. In this paper, we propose a new bearing angle approach. It is theoretically analyzed that the observability of this approach is significantly improved compared to the conventional bearing-only one. It is verified by experiments that the bearing angle approach works effectively in many scenarios where the bearing-only one fails. The benefits come with no additional cost since this approach simply utilizes the size information that has not been fully exploited before. We conducted a series of experiments to verify the effectiveness of the approach. First, numerical simulation. In case 1, the observer moves around the target on a circle. This is the most favorable case for the bearing-only approach since its observability is strong in this case. The conventional bearing-only approach works well in this case. The bearing angle approach also works well and converges faster than the bearing-only one. In case 2, the observer moves towards the target along the bearing. This is the most challenging case for the bearing-only approach since its observability is poor in this case. The bearing-only approach fails. Our bearing angle approach still works effectively. In case 3, the observer approaches the target by APNG law. This is a practically important case and many previous works studied how to improve the observability of the bearing-only approach in this case. The bearing-only approach fails due to its weak observability. The bearing angle approach still works effectively. We further conducted a sim-based simulation to verify the effectiveness of the proposed approach. The AirSim simulation considers more realistic experimental setups including visual detection and flight control. The results suggest that the bearing angle approach has stronger observability than the bearing-only one, which is consistent with the numerical simulation. In addition to simulation, we conducted a series of real-world experiments. The first is a handheld camera observing a ground robot. Consider the scenario where the camera gets close or far from the target periodically. In this scenario, the bearing-only approach works unstably due to the weak observability. By contrast, the bearing angle approach can work effectively. Finally, we conducted flight experiments based on 2 quadcopter platforms. We studied a MAV following MAV scenario. The bearing-only approach works unstably in this case due to weak observability, but our bearing angle approach works effectively. In summary, by fully exploits the size information of a bounding box that has not been well studied before, the proposed bearing angle approach achieves superior observability than the conventional bearing-only one.